Section 2.1, we're going to look at ways to describe location of a data point within a distribution. Okay, so the first way we're going to look at is called a percentile. That is it tells you the percent of the values in the data set that are less than that specific person's. All right, so we'll look at an example. Jenny scored an 86 on her test. How did she perform relative to the rest of her class? So here is everybody's test scores in a STEM plot. Okay, we know that Jenny scored an 86. So what we need to know is how many people scored less than Jenny. All right, so all these numbers in purple are less than Jenny's 86. That is 21 out of the 25 people in her class scored lower than Jenny. So 21 over 25 would be 84%. So we say Jenny is at the 84th percentile. All right, when you're asked to interpret a percentile, here's sort of the formula that we're going to use. Blank percent of, and then the context of the problem are less than or equal to the value, the actual number. So for Jenny, 84% of test scores are less than or equal to 86 because that was her test score. Okay. We can also work backwards from a percentile to find a score. All right, so we know that Ryan's score is at the 20th percentile. What is his test score? So what that means is 20% of the people scored lower than Ryan. And I know that there were 25 people in this class, so I need to know what 20% of 25 is. Okay, so 0.2 times 25 is 5. That means there were 5 people that scored lower than Ryan. So 1, 2, 3, 4, 5. So that means Ryan has to be the next one. So Ryan scored a 75. All right, because he is at the 20th percentile, which means he is better than 5%, or sorry, better than 20% or 5 people in his class. All right, something that we like to do with finding direction is construct what's called a cumulative relative frequency graph. It's also sometimes called an ogive. That is spelled O-G-I-V-E, so it looks like ogive, but it's pronounced ogive. All right, and so here's what we do. We would do similar to what we would do for a histogram, all right, and a relative frequency histogram. So we have the number of data points that fall in each range, and then we find those as percents, but we want this to be cumulative. So what we're going to do is I'm going to find cumulative frequency, meaning I'm going to add the next group. So from 40 to 44, there were 2 presidents. From 45 to 49, there were 7. So 2 plus 7 is 9, which means on my graph, from ages 40 to 49, I know that there were 9 total presidents. 9 plus 13, 22. And we continue adding the next group to get the cumulative frequency. And then we can do the same thing relatively, meaning turn those numbers into percents. And so anytime we do a cumulative relative frequency graph, the number at the end should always add up to 100 because we are including 100% of the data in our graph. So here's what the graph looks like. All right, the numbers on the x-axis are the endpoints of each of our groups. And then going up the y-axis, we have percentages. And so for 40 to 44, that's 4.5%. So I put a dot at 45 and 4.5%. Then my next dot is at 20.5%, and then 50, and so on and so forth. Okay, now some things that we can tell from this graph. All right, we can find quartiles and the median. Or at least an estimate of those things. So the first quartile is the 25th percentile. So I could guess about where 25% is on this graph, probably about here. And then if I go over to where it meets the line, that 25th percentile is going to be right here, probably around age 51. All right, the median would be at the 50th percentile. All right, so that's right there for us at 55. And then the third quartile would be at the 75th percentile, which would be somewhere around here. Okay, so we're right around that dot and maybe like 60, 61. Okay, so we could get a rough estimate. We could say the median would be around 55. I would say Q1 can be around probably 51. and then Q3 would be roughly 61, we'll say. So I can get a rough estimate of my IQR. It would be approximately 61 minus 51, or 10. Okay. The other thing that we can see is we can tell roughly the shape of the distribution. So if I go back and look at the table here, I can see that the highest numbers are in the middle, 13, 12. So that would be like the peak of my graph. And then on the left side, it's 7, 2. On the right side, it's 7, 3. So that graph would be roughly symmetric. All right. So if I look at the ogive, I have a short tail at the beginning, a short tail at the end, and then the steepest parts of the graph are in the middle. That is a sign that that graph is roughly symmetric. If the graph is skewed in one direction or the other, these little tails where it flattens out, they get longer. So if a graph was skewed left, I might have a longer flat tail at the beginning, and then the steep part and a short one at the end. So this would be like skewed left because I have this long tail on the left side. If I had a skewed right graph, it might like this, steep in the middle and then a longer tail at the end. So that would be skewed right. So we can roughly tell the shape by how long the tails at either end of the graph are. Another way we have of measuring position is a z-score. You might also see this referred to as a standardized score. All right, and so this is something you're probably familiar with. To find a z-score, we're going to take the value that we're talking about, subtract the mean, and then divide by the standard deviation. All right, so Jenny scored an 86. We already talked about her earlier. And now we know that the class mean was an 80 and the standard deviation was 6.07. So we're going to find her z-score and then interpret it, okay? So we're just going to plug those numbers in. Her score of 86 minus the mean of 80 divided by the standard deviation, and we get 0.99. Okay, and so when we interpret, this is kind of the formula that I want you guys to follow. That way you'll always get full credit. All right, the number with context. Okay, so her test, we can't just say 86. We have to say her test score of 86. All right, is whatever the z-score is, 0.99 standard deviations, and then you have to say above or below the mean. All right, anything with a positive z-score is above the mean. Anything with a negative z-score is below the mean. Okay, so the tip for you there is make sure you don't say away from the mean. Make sure you describe it as above or below. Okay. All right, and then the last thing we're going to look at is transforming data. Sometimes we have to change units of our data or some other scale, like metric system versus the US system, or Fahrenheit to Celsius, things like that. And so we want to look at when we have to transform our data, what does that do to our distribution? Okay, so one thing we can do is we can add or subtract a constant. All right, sometimes we have to add or subtract the same number to each value in our data set. Okay, when that happens, all right, we can talk about three things that it affects. Measures of center and location. So that would include the mean, the 5-number summary, percentiles. Okay, all of those are going to be added or subtracted by that same number. So let's look at an example because this might make it a little bit clearer. All right, so we have a group of students in Australia that's asked to guess the width of their classroom to the nearest meter, okay? And then the actual width of the room was 13 meters. So instead of putting their guesses, what we want to know is what was their error? How far off were they? So if we take their guess and subtract 13, that will tell us how far off their guess was. All right. And so things that we want to know, all right, here's what that would look like. So we took each student's guess and we subtracted 13. So now I know, these students that are close to 0 were close to the actual width of the classroom. These students guessed too low. These students guessed too high. All right, and so what we want to know is what is the effect on some different things in our data. So what shape does the distribution of error have? Here's the original. All right, our error, the one where we subtracted 13, it's going to have the same shape. Okay, so the top to the bottom, same shape, we just shifted it over a little bit. Okay. what is the mean and the median for error? Okay, the mean and the median are measures of center, so they are going to be subtracted by 13 as well. All right, so the mean of the original of their guesses was 16.02. The mean of the error is going to be 16.02 minus 13. Same for the median. We're going to subtract 13 to get the mean and median for the error. All right, and then the last thing, standard deviation and IQR, interquartile range. Okay, those are measures of variability. When we are adding and subtracting, measures of variability are not affected. So they're going to stay exactly the same as they were in the original. Standard deviation is the same, IQR is the same. Okay. The other way that we can transform data is we can multiply or divide by a constant. Okay, so we're going to look at the students guessing again. If we tell them that their guess, the average guess was off by about 2 meters, that doesn't really help them because they're not familiar with the metric system yet. So what we're going to do is we're going to take that 2 meter average like a mistake or off, and we're going to multiply that by 3.28 to tell us what the what their guesses look like, their error looks like in feet. Okay, so when we're talking about multiplying or dividing, measures of center and location, just like before, they're going to be multiplied or divided by that same number. This time, our measures of variability are also going to be multiplied or divided by that same number, and the shape of the distribution does not change. Okay, so here's the shape of my error. When I change that into feet, the shape is not going to change. Okay, it's going to be exactly the same, skewed to the right. All right. Find the median of the distribution. Okay, since we multiplied all the values by 3.28, our median is also going to be multiplied by 3.28. Okay, find the IQR. All right, when we are multiplying, measures of variability change as well. So we're going to multiply that IQR by that same 3.28 number. Okay. So to sum this up kind of in table form, because that'll be easier to remember, okay, the two transformations that we're going to look at is either adding or subtracting a number to each data point, or multiplying or dividing by each data point. Sometimes we can do both at the same time, okay? For measures of center and location, they get moved the same way. So if we added to the numbers, then we add to measures of center. If we multiplied, then we multiply. For measures of variability, there is no change when we're adding and subtracting. So this is like standard deviation, okay? Those things don't change. When we multiply or divide, they do change. And then the shape of the distribution does not change no matter what transformation we apply. Okay, and that's it for 2.1.